I work on a team that sort of does platformy things as we get bigger in scale in terms of like big data stuff. So I'm going to talk a little bit about Presto. Who here has heard of Presto? 3 people? Cool. So maybe this will be interesting, hopefully. So the subtitle of this talk is Querying Large Data Sets Without a Database. How many of you like run a data warehouse? Maybe if you're not familiar with Presto, but you run like a data warehouse or any sort of large data thing. Few? Okay. So hopefully be slightly more really relevant to you. Kind of talk about some of the stuff that we've kind of hit in the structure of where Presto is starting to be a really good fit. But more than anything, it's just a really cool system. As far as like new tech that's out there that I'm like, that's pretty sweet, gets my 2 thumbs up, Presto was one of them. So we'll talk a little bit about it, and hopefully we'll all learn something. And also, feel free to like interrupt me, ask questions anytime. I did this presentation like a week ago, actually at my work. Go ahead. What's large? Large, like petabyte scale, if you want to talk about, like really large, but smaller than that, right? So intended to be very, very large. At least that's the source scale. It's like, I'll get into that. But yeah, so feel free to ask questions. Like I did this presentation a little bit like a week ago, and in like 25 minutes. So I don't want to be done in 25 minutes, so please like ask me questions. I've made more content since then, but please ask me questions. So first, what is Presto? So this is just like from the prestodb.io website. Presto is open source distributed SQL engine. Interactive queries against data sources of all sizes, petabytes. So the thing that's kind of, the highlights out of here is, so Facebook made this. This is another one of their like open source projects that I'm just like, you guys are so great these days. Even though I hate your product. But it's really sort of to hit this use case of interactive analytics on really large data scales. So Facebook talks about how they use this. They have a multiple petabyte data warehouse that they use, and they run thousands of queries through this on a day. Netflix talks about this a lot too. And like their average response times across these huge data sets will be more on the orders of seconds to minutes, rather than your sort of traditional data warehouse. A lot of those data warehouse jobs taking minutes or hours, right? So it's really sort of trying to bring down the speed such that we can really get to this sort of interactive analytics for sort of this immediate feedback loops to get insights into your data. So people who use it, Facebook, since they wrote it, Dropbox is talked a lot how they use it, Airbnb, and maybe you. So we in the structure have really found that it fits like some really niche use cases that we've run to, just as we've hit at scale, and I'll talk about those later on. But like I honestly think it's a pretty applicable thing for a lot of companies. Okay, but first, like why Presto? Like why do you need this system that operates? And I feel like I'm gonna go over here. This is better. So my head like being blind sight. Okay, so how many of you would say you're like familiar with just like have dealt with data warehouses? Maybe you're not doing it now, you've dealt with it in the past. A good number? Okay. So this is pretty true, right? In the old world, like traditional way that we do data warehousing, you really get to choose 2 of these tenets, right? You get fast, scalable, or cheap. I'll let you work out what that means, but so it used to be if you wanted fast and scalable, you went to Oracle and Teradata and literally gave them millions of dollars. Like that's not like, oh, lots of money, like literally millions of dollars. So actually, George and I worked together at a company. We had a partnership with Nintendo, and they were talking about how they did some of their analytics stuff. They're talking about how they like were paying Teradata these millions of dollars, like crazy amounts of money to just put in. Really, this isn't like petabyte scale, right? This is talking about like hundreds of gigabytes so you can get these answers pretty fast. But you could load it in, right? Get another proprietary software, you could run some big queries, and you get answers pretty quick. And that worked. If you didn't want to pay a ton of money, you would use Hadoop or Hive. Hadoop or Hive are wonderful systems. They changed the way, like they really brought big data as a horrible buzzword, but they did do good things too. But you had to wait hours oftentimes to get the answers that you cared about as you kind of scaled up. So once again, like what changed in the world? Like why are we like kind of in this new realm of having systems like Presto? Basically, it's Google once again. So Google got like really big, right? Like super large. In 2010, Google releases a paper called on a system they call Dremel. Production since 2006. 2012 was when Facebook like first sort of talked about Presto and first started working on it. They didn't really like release a version until like 2013. And now like 2016 is getting stable enough. A lot of people are starting to use it. We've done the trickle down. And like once again, it's like the 10-year cycle of Google being 10 years ahead of pretty much everybody. But we're all blessed by their smartness, I guess. So like while this is happening, right? Like while we're just getting more massive amounts of data, like SaaS is now the norm, right? Like everybody's building these SaaS apps, and you start to go get money from VCs because you said SaaS in your thing. And you move to the cloud, right? And then there's like this weird side effect of like SaaS in the cloud, which is just that even operationally, you now have just massive amounts of data operationally. Instead of having like your like 20 servers that you like gave names to and you hugged them very tightly and loved them, we just like had a ton of servers that would be up and down, and you might like scale up to 500 servers a day. Anyway, you gotta capture all this data, right? You have logs, system metrics, et cetera, et cetera. And you know, SOA microservices, like those aren't new, but they're just, you know, sort of, they're coming into their own once again. And they just bring more data and more different types of data. So like the traditional data warehouse, if you've like worked in this realm, you'll feel this pain. They're like all relational, right? They sort of assume, like they sort of operate from this perspective that like, oh, you have like your app, and that app has your data model, and we transform that data into a data warehouse, and we're done. But that's not as true anymore, right? Like, hey, you've got all this data that is now your operational data, right? Your metrics, logs, maybe documents from more like a full text store that were not necessarily relational, right? And it didn't fit as well into like this one sort of static data warehouse. And as you go to microservices or SOA, like maintain the upfront work you have to do of each one of these new services to also write into your data warehouse and to like join properly in its relational model becomes really difficult. You have a high upfront cost to get there. So like, if the last few years people have started to talk about this concept of the data lake. So a data lake is this sort of concept of, rather than like going and shoving everything in some database, like literally a database, whether that was Oracle Teradata or you know, a whole bunch of sharded Postgres things, you would instead write this data out to some storage place like S3 in some flat file format. And then at query time, we can kind of, in this world of the data lake, or data mart is another like word for this, pull in the different data sets you need to answer the question, and sort of at query time, do what you need to like get the data you need resident so that you can answer these questions. But obviously this has the challenge of now you can't just go and like have this single interface to your data warehouse, right? Like you lose the great power you had back in the day when you paid millions of dollars to Oracle or Teradata to sort of have this like one interface, and all your analysts and everybody could just go and hit your cluster and go and get their questions answered. So in like the TLDR of that is like, in the same way that monolith like microservices just sort of take this monolithic pile of stuff and break it into small piles of stuff. Like the way the data warehousing world is going is we're moving from like the one giant data warehouse thing to piles floating in a data lake. And if you work with that, maybe that makes sense enough. But okay, so really like what's Presto? So we're gonna look a little bit at the Dremel paper, and I know we're not gonna talk about like this is a paper where it's really great paper if you want to like go. And I'm not really gonna talk about the paper, but so this is the abstract. I'll give you guys just a minute to read that. So there's kind of two topics that they sort of talk about here, other than trillion row tables. Is they sort of talk about a multi-level execution tree and a columnar data layout. And then they sort of reiterate that about their columnar storage system. as well as running it across lots of nodes. So really, what Dremel sort of talked about was two things: a query engine, execution engine, and a columnar data storage format for like on disk, right? So we're going to kind of look at what those are and what makes Presto be Presto. So this is the high-level diagram of Presto's architecture. Like if you've looked at parallel relational databases, this should look fairly familiar. Our workers sort of take data and they sort of upstream results to some intermediary, and then we have like a coordinator thing that does all the work of query plan, execution, and scheduling. This is look very familiar if you've looked at, not necessarily Hadoop as much, but definitely Spark, definitely other big data systems. So before, we're going to step back a bit though, we're going to kind of like talk about what this means in theory. Like if we could just sort of, I guess to put it another way, like this isn't actually, this isn't like fancy new, right? Like these sorts of query engines have existed for a while, and they're actually relatively simple systems. And so we're going to kind of go through and talk about how you would build a query in a system like Presto that does this parallel query execution. So we're gonna pretend that we have this table stored as a CSV. It's kind of an important point here, but it's basically like some group membership, right? So we have a group name, and then these users that belong there. And each one of these entries is, that user is belonging to that group. And we've already done we're assuming this data warehouse. We've already denormalized some, right? Like we've made a really wide table. We've denormalized a whole bunch of stuff so that we can just sort of look at this one table and answer most of our questions. It's big, right? Like 100 billion records, like big table. So let's think about how we might want to answer a query. So let's just do this in the language of SQL. So we're going to select the group name and the count from this groups table, where filtered by a predicate of group names of engineers or friends, and grouped by group name. So basically, we want to see how many people are in engineers and in friends across this 100 billion table, 100 billion record table. You guys can probably figure where we're going to go here, right? Like we just can't do that work in one chunk of time. There's no way. So we distribute the query. Let's pretend we break the CSV arbitrarily up into three equal-sized files. We're going to append like a shard column to each one with just like the number of the shard. And we pretend we just rewrite the queries. Does this make sense, right? Is this like a sane approach? Okay. So we've now done, we say, okay, we're going to select group name from groups or shard one, group name. We take all those, we take them, we do the work in parallel, and we get like back a chunk for a shard, right? 100 billion records, that would be really sparse, but hey, maybe that's like realistic results, right? So we do this work, get these results per shard. We have to roll up these intermediate results. Did you have
no, I was scratching. Sorry.
It's okay. No. You can scratch your head all you want. I might just point.
Throwing you off.
Yeah. So, this is pretty straightforward. Like we know that there might be duplicates, or we're expecting there to be duplicates since we filtered it. So we, aggregate, union all the results together, regroup by name, and take the sum of the groups, right? Pretty straightforward way to sort of distribute that. And like this should run 3 times faster than just running it over once, right? We've parallelized by number of 3. At 100 billion records, that's probably not enough, right? But let's just, say we did 1,000, right? Like that's pretty easy fix. Like 1,000 shards, we're gonna get like 1,000 times speed up. But still, at 100 billion records, we've still got a lot of problems, right? We're still reading a ton more data than we actually care about, right? Because by storing it as a CSV in a flat file format, we have all these extra fields, like they're all stored, a row is stored next to each other. We don't really have a way of like just reading the subset of the data we care about. So that's harder to fix, right? And then depending on like the shard scheme we choose, like how many shards we choose, we sort of have this problem where it's like, well, this is a large amount of data, right? Like, am I getting the right amount of aggregation in my at my leaves of my tree, if that makes sense, of my query execution?
Maybe all the engineers are on one shard.
Exactly, right? Like there's a lot of things here that So you may be scheduling a ton of stuff, and you don't know if they're gonna be like your roll-ups are gonna look correct, or you're gonna get tons of skewiness such that like in your stage, your intermediate stage that kind of aggregates these things is gonna blow up there, right? Because if you make your shards too small, you're just doing a ton of extra like bookkeeping work. If you make them way too big, you're not getting good parallelization, right? There's this really hard trade-off. And we have this predicate we're filtering by, and we are like pushing that down to the leaves of the nodes, but we still have to read all the data, right? Like we don't have an index in this case. So we're still reading in all of the data. So that is essentially like, this is the same way that Presto works. Presto doesn't necessarily have, like, at least given the case of reading stuff from CSV, there's not much more you can really do there, right? Like there's just not a lot of magic we can do. But if we introduce a better way of storing data, we can actually do way, way better than this. First of all, the most obvious thing, how many of you like have worked with columnar storage systems? Okay, most of you probably have like read some of the benefits, right? Like, especially when we have wide columns like this, which oftentimes that's part of the course in the world of big data, is these really wide columns with really wide tables with lots of columns. And we're only selecting 2 of like those 50 columns that we had, right? So rather than having to read in all this data from each and every single, and then basically read in a whole row and then cut out just a small slice of it, if we store our data in a columnar fashion, we can instead, sorry, this is like one of those cases where I should just use a separate slide, but I wasn't that smart. Instead of like, so if we want to just worry about these 2 columns, by having a columnar storage system, we can just read off.
There's like right click, it's a web thing.
Oh, hey, George. Man, this guy.
Whoop.
Oh, it was up there.
Oh, man, it's still small, but we can do this.
Bam.
This is the problem with using Markdown slides.
It's better than LaTeX.
That is true. I still love you for it. Keep on doing it.
Yeah.
So this is just kind of give us the example of here. We sort of take these rows, we break them up, and we then store them sequentially on disk by the values in the column.
So,
right.
So the 2 squares in one column represent row storage in the left column.
This is up above is rows, right? So we have a row, and when you see it, when you're trying to pull the values in a columnar way, this is your disk access, basically.
Oh, okay, all right.
And this is what your disk access this is like its layout in terms of columns.
So
and this is your disk access.
The row is rows.
Yes.
First row is row.
Yeah.
The second row is columns.
Well, this is still rows, right? But this is like your this is your data you're caring about.
The storage format is columns.
Yeah, exactly. Is that cool? Okay. So I just need to remember this one. Oh no.
What have you done?
Everything.
This is all you've heard, George.
Yep. Cool. So yes, by storing stuff in a columnar way, we can solve one problem, right? Which is instead of having to read crap ton of data, we can read data. We can read just the portion of the data we actually care about.
So that's true if we know that that's the way we want to read the data stored.
Yes, you are taking the trade-off that as soon as you say, I want to actually select a lot of fields out of here, you're playing the trade-off game, right? Like you're sort of starts now saying, oh, if I'm trying to select 35 of my other columns, your disk access is still going to suck, right? Like it's actually still going to be better than if it's row oriented, right? Even if you're selecting 35 of 50 columns, but as soon as you try and select everything, I mean, either row or column oriented, it's still going to suck.
I was just going to say, I think you're talking about dynamic queries, but I was going to say no, because you just index all the stuff up front. So
I mean, yeah, I mean, in a lot of ways, like, columns sort of also do away with some of the need you have for certain types of indices because you kind of have, anyway, I won't get too much into that right now, but go look at how Cassandra stores data. It's kind of a trip. Anyway, so this is nice, right? This is like the first big win we can do. We flip our view of the world. Now everything's stored in a column-oriented fashion. But that still only solves like one of those problems. We still don't get anything in terms of like how do we do this scheduling? That's still hard. Sharding is still hard. So by introducing statistics on this data, right? Like so next to this data, if we then sort of imagine that we have statistics about, hey, you know what? This chunk of data, this next chunk of data on disk, its ranges, its min and max are this. Its amount of size, the number of bytes are this. The number of rows are this, right? There's a few statistics that we can pull in there that have a very low amount of storage on disk, but introduce a lot of flexibility once we make a scheduler smarter, that we can then say, oh, hey, you know what? The scheduler can look at that ahead of time, know how much stuff, how much space is each shard or partition is, and make more intelligent decisions based upon that, right? We can also like make our decisions of sharding a lot easier. This image is important, but essentially, like if you think about the way you're kind of might be like sharding that data, once you if you have something that's sort of aware of this and these statistics, we can sort of make the decision to sort of treat maybe 6 small shards that are all neighbors to each other. We can sort of say, you know what, still schedule that as one chunk, right? Like that's still like one chunk of schedulable work to do. And that works better for like our upstream process, right? So there's a lot of like tricky things we can do when we introduce these statistics to sort of make that scheduling problem nicer and happier. And more than that, right? Like we just like had a CSV, let's say we gzipped it, but now that we're storing things in a column-oriented fashion, we could actually sort of say, hey, how about for this array of what is just ints, we can use a different compression algorithm for that set of ints that is going to be more efficient than just like a straight up gzip, right? Like we may do a bit packing encoding for that set of ints because we know the range and the min on it. Especially with statistics are there, right? Like if in the statistics you say, hey, the range of this is 0 to 120 or 0 to 127, why are you storing this in a big int, right? Like we can do some really great bit packing to sort of drop down that size massively. And while this is normally those sorts of things where, oh, who cares? At these sizes, that like cutting down in half of a single int can save you on the orders of gigabytes, right? Like of space. So we can really choose actually like a per column compression and encoding to make that optimally sized on disk. So we have to read as little back as possible. And we can even do like some other tricks, right? Like for really low cardinality fields, not really low, we can actually just say, you know what, there's only like 3 different values that exist in here. What if we just store a dictionary of all the values that actually appear in this like partition of the data, right? So that when you're coming through and you sort of say, hey, I've got engineer and I look at this portion of the section of the data, I look up in my dictionary and say, oh, what? Guess what? There's no engineers and there's no friends in here. I don't even need to care about this group. I don't even like read this off disk, right? It's not necessarily like, that's almost starts to be a little bit in the terms of what an index gives you, right? It's still not an index. You still don't have like a full proper index, but you sort of start to get a little bit of this hint of, hey, we can actually store some stuff on disk that's not a huge amount of data and get really good wins and give some more scheduler.
So there's still that initial read where you put it in that shard though, right? Like you're not getting away from that initial.
Yeah, you're still gonna have to like store it in this.
Right, like you start flat, but then to start work on it, you do the initial read, put it in the shards, and then you can do interactive queries that maybe don't use.
This isn't
shard.
on disk format.
This is the on disk. This is, you would be storing it this way.
You would be storing it this way. You store it this way. So we store those statistics. So we compute all that, right? As we're writing out that data, we keep all these statistics, store it, compute that all for the data, and then like leading into that, one of the things we could do is then we could actually store those statistics and metadata separately. So then when you want to do when you're the query planner and you want to figure out how to query this stuff, you don't have to read all the files or kind of scan through them to figure it out. You just read the separate file, right? It tells you where all the partitions live, like where they physically live on disk. lots of other fancy things. You can sort of make that really fast. You just look at that metadata file, get it, and then let the query planner just use all the metadata to then make the query plan, so you actually don't have to read anything. You get a very optimized query plan, only having to read a small amount of metadata. And then we use something like Thrift. Makes this really nice across different languages, whether or not you like Thrift, it's a whole thing. So anyway, lots of tricks we can do. So Google in the Dremel paper, they talked about kind of a disk storage format like this, and then the open source implementation of that is called Parquet. So this Parquet, so Parquet is just a binary on-disk columnar serialization format that has metadata and statistics and other fancy things that make it so you can use a query engine like Presto that's aware of this Parquet format and get much better query execution speed. So I kind of, like I said, once again, like this isn't an index, right? Like this is not a database index, like that's just stored on disk. But depending on like some of the way we can see, if you squint hard enough, if that makes sense, it kind of gives us some of the same power we kind of get with the database index. Like don't go say like, oh, Presto uses database indexes by Parquet. That's not true. But like logically we can sort of say, hey, we've got some of this stuff that at least helps us to filter down the amount of data we actually need to read so that our queries can get much, much faster. So this is like the Parquet storage format. I don't know how much you guys care about like low level, but it's pretty interesting. It's very novel. The other really interesting that I didn't even touch on here is this actually supports, Parquet also supports nested data structures. That was actually the big thing that Dremel sort of brought to in their paper, was to a really compact way of taking like something like JSON, right? Like maps, hashes, whatever, and representing that in a very efficient mechanism. So they kind of shred the data up such that it's stored in this columnar form, and they just need like basically like a small, like a 8-bit.
I assume for Dremel it's protocol buffers.
It is protocol buffers.
Everything is protocol buffers if it's a Google
it's just a
paper.
protocol buffer.
Yeah.
Yep. So it's just a special. At Google, it is literally just a protocol buffer with a special structure.
I think probably Google is just protocol buffers. I don't know that Google does anything besides protocol buffers. Like all of their stuff is just moving around protocol buffers.
It's protocol.
That's all.
Why would they use anything else?
Well, I'm just saying they don't have any other code. Like it's just protocol buffers.
At the lowest level.
Yeah,
it's just protocol
right,
buffer.
right. It's become
All the way down
self-aware,
protocol buffer.
self-aware protocol buffers.
But actually, he's totally right. In the Dremel paper, it's just a fancy way of storing protocol, or like formatting your protocol buffers. You can get into details here. They have like repetition levels and depth levels that basically allow you to sort of take this nested data structure. But it's really nice because you can sort of, this sort of is part of the thing of like sort of the new non-relational or not everything relational world. Parquet is also a very good storage format for that, right? Like you can take this deeply nested structure, throw it into this Parquet format, and still query it against it in a really like logical, fast fashion. Some other like novel things that they did, like everything in Parquet is thought out by like somebody really thought about this crap. So actually, if you want to grab this metadata, you can either store this separately. So all these things, all the different like types can be stored separately, which I'll show in a minute, or they can be stored in like one big file. And then actually, if you do store it all together, you actually store like all this metadata at the end of the file. And there's some really reasons why that's actually really nice. Like
Why at the end? Because then you don't have the byte count to jump to.
so you can get this still off the disk though, right? Okay. And then you could scan forward just off the disk, and then it's actually optimized for writing out faster, because then you've written everything and then you write it. But so like anyway, so here's like some of the metadata Keith talked about. Like we'll actually I have kind of a so like I said, this is so this is actually, since it's Thrift, like, I don't know about you guys, but like binary data formats are really difficult to like kind of wrap your head around. You can't just like open it up and be like, oh, I can see that. But since it's Thrift, I I just wrote a little script that generated some JavaScript code for deserializing the thrift stuff, or I didn't write the code, I just had thrift to generate me some code. And this is the way, and then I just grabbed the single metadata file for this data, and we can actually just go through there, like you just look through it and sort of see what, so this,
Can you make it larger still?
yeah, I certainly can. And I also should change my like contrast, because that's not super awesome on the giant screen. But so the schema is encoded in here, right? So I don't know how, like, if you've used big data systems, this is super nice to have the schema encoded into the metadata. Like, really, like the state of the art for a lot of big data systems is still like CSVs, right? You just have like all these problems with positional things. It's the worst stuff in the world. Like that's not. It's kind of lowest common denominator for a lot of stuff.
But unlike JSON, you're not actually encoding the name as part of your data.
Right. That's like the big thing with JSON. Like, we really don't want to like that cost of the keys is non-trivial at large data sets. Like, even though you can say, oh, well, gzip gets rid of most of it. Kinda, right? Like, you're still taking some overhead. It's going to be on the order of gigabytes or terabytes, right, for large data sets. So the schema is encoded in there, and then the cool stuff is up here. So I said that it was columnar. It is, but it actually stores like a group of rows together. Like it's this concept of a row group, right? And it may be, a million or whatever, however big it wants. You kind of tune it, and then in that row group, then it is stored columnar. Does that make sense? So this is very common actually in columnar systems. We don't like go full bore columnar because there's issues with that. Like if you have one really large column of text, right? Say like you have a very long text field, suddenly you've got like a much farther scan to like get to your next set of data. So we store a group of rows typically together, and then within that group of rows, then it is columnarly. I don't know if that's a word, but go ahead.
So the rows is it one file?
Yes and no. Like, so I'll show you what this actually looks like. So this is a row group, and it actually says, hey, here are my columns, and this is the path to this other file. So in this case, this is stored in S3. It's just going to be another S3. Part of a pointer in S3. And then this is the offsets. So this isn't the metadata, right? This is actually not the data. This is just the metadata. It gives me the file offsets to read from there. So in a lot of, for all intents and purposes, you kind of don't care as much because they keep all the metadata for you. And then like Presto will do range requests, right? Like even if you need to grab a column out of the middle of something, it will use the metadata to do a range request against S3 to be just the chunk of data that you care about. So yeah, the metadata not only, well, I'll show you some statistics here. So we can look at a row group, we can look at a column. So let's just look at our ID column here as the first one. We can sort of see some of the metadata that keeps around. Don't need to dig into this, but this you can go, like these are the encodings and types that it has. It gives you, so in, like one of the statistics that it keeps is the number of values, right? So like the number of rows that exist in this different column. Or maybe that one might be distinct values. So number of somewhere. Anyway, keeps you basically track of like, hey, this is how many for this given column in this given row group. Here's how many values there exist there. And that may not be the same as rows because it doesn't store nulls unless it has to. And then we get some statistics in here: max, min, null count. And I don't have any in this data set, but this is where I was talking about those dictionary pages, right? So I'll have an offset to say, hey, if you want to get the dictionary, here's the offset in the file to go grab the dictionary page. So you can just pull the dictionary page to kind of get that sort of really index stuff happening. So does that kind of make sense, like how Parquet sort of stores data? Roughly give you an idea of what that looks like physically. So now that we have, a format like Parquet, this is where we really get like the nice fanciness that Presto gives us. So let's like take a look at that query again. Now with the world of Parquet as our data storage format. This will be actually like specific to Presto. Presto actually doesn't like want to, it just is just the query engine. It actually doesn't really care about like where the metadata and whatnot lives. So we actually use the Hive meta store. I'm not sure how many of you would work with Hive, but essentially the Hive meta store is sort of this, like you could almost say it's analogous to like information schema in Postgres, if that makes sense. It's like all the track, it's not like actually your data, but it's just keeping track of all of the stuff about where your data is. It's the meta store. So you actually tell Hive and say, hey Hive, here's my database and here's my table. With actually it's really annoying. Right now you still have to put in Hive, you still have to actually list the schema again, even though you shouldn't have to. But so right now you still have to like list your fields, but at some point in time you'll just say, here's my table stored as Parquet at this location, right? So you've told Hive, hey, here's this database table. It's in a Parquet format, and here's its location on disk. Hive goes and pulls that down, and then you're good to go. And then in Presto, you say, hey, Presto, I'm using as my connector or my catalog Hive. And then, so we have this query that we're going to run by Presto. All like very similar typical SQL syntax. And then just as before, Presto's we're going to build a query plan, but now we're going to use Presto with that metadata that we're able to grab out of the table to sort of say, hey, it looks at the required columns, the row group counts, whether there's any dictionaries that it can use, and partition statistics to determine a very optimal plan. So at this point, you can sort of figure out, hey, you know what, I actually have to read 1/10 of this data, and I know exactly where they are. Like I know exactly the offsets on disk that I actually need to go hit from, so we can get a very optimal query plan using this metadata. And it will do the best thing in terms of okay, do I need just one roll-up stage? Or is this so big that I'm going to need multiple cascading roll-up stages to make that work? In the execution, the other really nice thing is that it's also like a streaming. This gets a little bit into, I think if you're at the Spark Meetup, this will make a little more, this will kind of sound familiar to you. But, so we have this tree of execution, right? The leaves are our kind of work to be done, and then we have some level up that aggregates and so forth. Each of those levels or depths in the tree is a stage. And much like Spark, it's sort of the next sequence of work to be done. But unlike Spark, they can be run concurrently, meaning that as soon as results are starting to be finished out of one leaf in that stage, the aggregating of in the next stage can start doing that work. Does that make sense? Good, decent job of describing that. So as it says in there, as we finish collecting the counts and leaf notes, we can start aggregating as soon as it's ready. This is also another nice one that it gives you. And then, we finish aggregating the results, we're pretty much done, and really will be pretty fast. And it's really good. So I'll talk about a little about how its structure has starting to, we're still really new with Presto, but it's looking more and more like it will be one of the kind of nice tools in our tool bag.
Question.
Yeah.
So, what's the advantage of having break over to the file? What's the expected rate to measure what?
In a why do we do that rather than purely columnar?
Yeah.
The biggest reason, I wish I had a whiteboard. I almost thought
We can make one.
No, it's cool. The biggest reason, is if you imagine, even though we may have 1 million rows, say we have this is the typical example is you have one text field that on average length is a meg, right? Suddenly as and this really has to do more with some of the spinny disk thing, back in the spinny disk days, right? Suddenly you have this large chunk of the disk you have to scan through. That's for this one really long column across the disk. It takes up a ton more data. The other reason is that a partitioning column for data is sort of ends up being rows, right? Because you need that data sort of resident to each other if you're going to start partitioning it. So most of the columnar storage systems do have some aggregation of rows, just because you sort of need that partitioning to come in. And I don't know, it's kind of weird to think about how you would do a partitioning of data it's not on a row boundary. That's what makes sense.
If you did purely columnar storage, and then asked for all the fields for a given row, that's going to involve seeking across potentially
That's also-
all of the columns, right? Because since the columns are ordered, all the data is stored in per column. To get all of the data per row, it's going to be like having to read all those column formats. So if you do the row, it sort of bounds the variance of how much data you have to go read.
Yeah, so you kind of get that. It sort of helps with that worst case scenario of you reading all the data in the like wide query selection. Have any of you here used Redshift? Okay, one. So Redshift is great. Redshift is a wonderful, this is actually one of the first things that sort of started like making the oracles and Teradata's kind of like actually have to earn their living. Amazon came in, released Redshift. Redshift is like a columnar database, distributed database that it's actually based on Postgres. It's a really great system, but for our use cases, like we have hundreds of gigs daily of new logs, right? And we use our logs for a lot of stuff. That's how we kind of derive usage data. A lot of stuff kind of comes out of our logs. So every day we're like adding, 100 gigs of new logs into these servers. And they were and we would load them into Redshift, which is, an expensive operation to like load them into a database. And we have to keep scaling that up, right? And really it was only getting used like a few times a day, right? Like there would be sort of like this, like, oh, I gotta go, like one of our analysts or finance team have to go and say like, oh, I gotta go like answer these questions. They go do it, they go run like their, 10, 20 queries or whatever, and they're done. And the rest of the day, that cluster basically sits there, right? But we have to keep that cluster around because we have to, like, that's the only way we were able to get like good performance to answer the questions fast enough, was to keep it in this format that, builds indices and keeps all this stuff in disk and memory. So we're starting to move that to Presto with Parquet formats. And we found that like, we're getting like 80–90% of the query performance across most queries. And we can just spin up that cluster when we need it and then tear it down like as soon as they're done, right? So it's like, yeah, we have a 15-minute sort of startup cost while we bring up a cluster. But after that's done, we get most of the same query performance, and then it gets shut down and we save a lot of money over having to keep this cluster up all the time. And this is really true of a ton of people's like data warehousing needs, right? It's like you kind of paid all this cost for these systems and you kept all this stuff in memory and like with having it build indices so that you could get fast performance, but you just didn't use it that much. So that's like our first foray into it. We'll probably have this migrated to that pretty completely in the next month or two. And since it's like our...
Can you explain, I think I know the answer, but can you explain why you're saving money again? Like where are you moving the data?
So we're moving the data to just living on S3
Okay.
instead of having it live like in a cluster of machines that, well, it's Redshift, so you don't have like tons of inspection to it, but essentially on its physical hard drive in Redshift, right?
Where do you run the queries?
We spin up an EMR cluster, so an Amazon Elastic MapReduce cluster, and we'll spin up way more machine, right? Like so right now our Redshift clusters may have 20 nodes or something. We'll spin up 100 nodes. We'll only use those 100 nodes for about an hour and then tear it down.
Okay. So your savings comes from the combination of not having to keep all the data in Redshift instances that are running all the time.
Exactly.
Combined with only actually doing the queries.
Exactly. Yep. And the nice thing is due to the way like that some of this works is if you're like using, depending on, you get a lot of, I didn't really talk about this, but there's a whole bunch of ways you can sort of store this data with very specific partitioning, right? So for log data, the natural partitioning is by like dates or months, right? We could actually just like take whereas Redshift, we have to keep all the data sort of in this big giant Redshift cluster. You can sort of just, if you only need to look at like one day's data, you can use a very small cluster and just use the on-disk like layout where you say like, oh, this date is for this year and month and whatnot. And just spin up a very small cluster if you just have a small amount of data, partition of data you're just looking at. So it also gives you a lot more sort of granularity with the data that you may not have with something just where you only get like one storage tier with Redshift.
So question.
Go ahead.
So I'm a little confused about data storage. So Presto has connectors to things like MySQL. They're not columnar.
Right.
So is it copying the data out?
Yes. Yeah. So it will pull in the metadata to say, okay, this is what you can tell me about it,
Right.
and then where applicable, it will do like basically predicate push down. So rewriting the query such to say, only give me back the data that I need. But when you're using those connectors like MySQL and the Postgres one, you're not getting like that massive parallelization out of it. It's more of its niceness for being a federated access layer.
I see.
Right.
So if I'm doing massive aggregations, in that case, it's still going to do a table scan in MySQL.
Yeah.
That sucks.
Yeah, I mean that's really like so if you're doing that, like so this kind of gets back to the idea of like Presto kind of gives you this like one interface, right? Of you can answer all your questions. Like Presto is your single interface to interact with the data. And it's great because now you can also have this like
Right.
interactivity with your other systems. But yeah, like it's not going to be magical in terms of making your.
I thought maybe it was copying it out, putting it in a columnar format, storing it on its own.
No,
somewhere
it
else.
just like doesn't.
Okay, so if I want these kind of results, I have to, my storage has to be columnar.
Yeah, you basically have to sort of move to say, I'm going to do like an ETL that takes my other data, and gives me a view of it in my Parquet world, and that's when you get like those really big methods. Although, like that said, like being able to run a query against Postgres and MySQL, I don't know for those of you who did like, I hadn't mentioned this yet. All of like the interaction with these, what Presto calls catalogs, happens through these connectors. So it's this pluggable system that basically says, hey, I want to run some queries against Postgres. Oh, now I want to run some queries against MySQL. Oh, and actually, you know what? Right now I want to run a query against Postgres and MySQL, right? It will actually take both those data sources, allow you to join across them. But that's just like an extra like nicety around it, sort of federated data access to multiple systems. So where we're going in the future, so we're moving to microservices, and like you don't realize like once you kind of, I don't know, has anybody tried to break down a big monolithic app like at scale? Okay, it's really bad. Like, I mean, it's really great, but it's really, really hard because there's all these concerns that sort of get taken care of transparently to a lot of teams, right? Like most teams don't realize that there's a BI team that's sitting here using this data, and you sort of have to still give them an interface even when you migrate a subset of the data out to a new system. So a lot of our work, particularly on my team, is trying to like get out ahead of that enough that we can sort of start laying down the track for as we get more and more microservices around to be able to like transform those all into a data warehouse that will work. And like I said, that one single interface is going to be a great choice for us to kind of hand to our BI teams. Another crazier thing is so we're an education company, and education like is all about analytics right now, for better or for worse. Like building dashboards and reports, like right now is one of the hardest things that we have to do, right? Because we're like now a pretty large scale company. We're not far enough ahead, right? Like we're not so microservicey that we can go and get a transform on our data and go and write a report in the right data format, if that makes sense. Like it's very difficult to do that. So at some point, like we hope to have all the data that we ever want to report on in some sort of flat file format, and maybe one of the ingredients to sort of a customer facing analytic solution would be Presto. There's like with some caching around it, you could do some pretty actually amazing things. Although that's not its traditional use case, we're kind of seeing if that will work. Okay, federated access. I do talk about that a little bit. So how long have I been talking here? You guys bored of me yet? No. Okay, 45 minutes. I've got like a really short demo. It's not going to be very impressive, but hey, it's still a demo.
Yeah.
So like I said, this is NeoMar cluster. That's how we've just.
Have you guys actually mapped all your data into a columnar format yet, or is that an ongoing process?
We do, but like ad hoc, if that makes sense. It's not like we have all the processes in place to do it. We just haven't we don't do it like on daily, if that makes sense. At some point, we will move all of our. So I'm not like the team I'm on also does all of our ETL, and at some point we will move our internal representation to Presto, like that are kind of all on the pipe will be Presto, or sorry, Parquet. And then once we do that, basically the last step, we basically hand out this data to customers, like one of the things that we do is we take all the data and we give them flat files. We'll kind of keep the internal representation as Parquet, and then the last step we'll serialize it out to like a CSV flat files that they can use. But I have some data here. So like I said, one of the things we do is you still have to like,
Larger font, sorry.
oh yeah, sorry. From here, it looks great. Is that legible?
Yeah.
So like, so this is just a Hive script. Like, so one of the annoying things right now is you still, is that like cut off on one? You still have to sort of give your schema. So this is just like our data warehouse format that we have internally. We also expose to customers, but so this is just what I showed before. We sort of create all these tables, point them in. So this is just Hive SQL, and then we just hand this into Hive. It'll execute all those, and then once that's done, we then have Presto. We then start Presto. Catalog. This is how we kind of get that federatedness. You can switch between different like backing stores. This one is called Hive. And then from here, we just have like a pretty plain Jane. Just gonna use something else. So, okay. So first, like, let's compare just like some raw silly numbers to Hive. So Hive is built on top of Hadoop, for those of you who are not familiar. It is also a distributed query engine, but it's slow because it's built on top of Hadoop. Hadoop is slow. So just to kind of give like an idea of raw performance, we're just going to do a count. This is kind of this is like our internal wikis. That's just for a few of our like public facing things. So you're gonna see Hive is gonna do, Hive like maps all these things to traditional Hadoop MapReduce jobs. And while that's running to, let me start Presto.
Not going through each other.
They might, but we'll deal with it. That's just like this one. This is just doing a count, and it took 31 seconds. And we'll do that same count here, and we're done. This one's cheating, right? Because we have statistics. So we just looked up the statistics and said, oh, hey, that's the row count. But maybe more interesting is sort of like raw speed and actually doing something that's going to force us to read everything on the disk. So this is like the actual, what this is, this wiki page. It's actually like all the pages that exist in sort of our wikis that customers interact with. And this is just, we're going to take the max of all of that data. So this is going to force us to at least read that entire column, and it's like big long text fields. So it's an interesting idea to just see how much like data throughput we can get. So this is going to be with Hive here.
Finishing a solid state.
This is reading off S3. So this is all based off reading off S3. And this is like 15 gigs of data. This is not like big data by any means, but I can't use all like our actual customer data for this stuff. So I was like,
Can you run a query for all the credit card numbers?
yeah. I don't know. I don't even know what's like watch how to do this, but I guess I already started it. Okay, so that's like our maximum. That's our longest column, right? But it forces us just to show like, yeah, it forces us to read off everything.
What's a realistic performance increase you're experiencing from what before you started migrating to how long would it?
So right now we're using Redshift. For most of the stuff we're using now, we're using Redshift, so the performance is about the same.
Okay.
But for for some other workloads that we're like sort of experimenting with it, Well, so we haven't really used, we don't use Hadoop very much. We use Spark, and Spark and Presto sort of have like some similar views. I can get into, that's actually something I kind of want to talk about. So if you notice, Presto is great, love Presto, but really like a lot of the magic exists in Parquet, right? And so a lot of other big data tools are starting to support Parquet. So in where we use Spark, which is for our big, like much longer running jobs, right? Like maybe one of the, oh yeah, I have a slide on that. As far as failure scenarios, they're the coordinator. You only really have one of those right now, and it's a single point of failure. And it's not the worst thing in the world since it's just like, it's kind of almost, it's not stateless, but almost stateless. There's not much state there. You can swap them out pretty quick. But also, like if your workers fail, the query fails, right? This is a very different system from MapReduce and/or Spark that are these very fault-tolerant systems, right? Like this is kind of the sacrifice that sort of Presto makes, is to say, hey, I'm optimized for queries that maybe run in less than 10 minutes. So your cost, if we do lose a node, like if we do lose something and have to restart over, is quite low, right? Like because these are for interactive, like this interactive sort of analytics. Whereas the systems like Spark and Hadoop are very much intended for much longer running jobs, like across more data, right? So by no means is Presto like going to replace our usage of Spark or another company's MapReduce or Hadoop, but they really kind of work together well. But that said, a lot of the things that Presto is like, these distributed query or engines like Presto, they're highly parallelized, are actually sort of bleeding into things like Spark. So Spark is going to have their 2.0 release, and a lot of things that Spark 2.0 are going to do look a heck of a lot like what Presto does. And a lot of that is powered by like properly storing stuff in columns in the most optimized way. So actually, like Spark's internal representation that it uses in memory looks a ton like what Parquet looks like, without all the statistics and that's somewhere else. So like the world of big data things is getting really interesting and really fast, right? Like most of where the things are headed towards these days is really about dealing with massive data sets quickly and moving towards like not the traditional world of big data being very slow. And sort of it's like the more real-time big data, right? And it's pretty fun stuff. So like I'm not the best person to answer about performance differences, but they're quite large. Right? From like some of these queries that you may have taken 10-minute Hadoop jobs will be 5 or 6 seconds. Netflix has some stats on the way that they use Presto, and they run like 4,000 queries a day or something, and they say like their 90th percentile is like less than a minute. So 90 above, it's like a minute for Presto. So it's quite fast for them on their petabyte scale for the warehouse. So anyway, that's about all I got. I almost took up an hour. Any other questions? Like I can talk about this for a while longer. Go ahead.
So you mentioned as a use case, you really use this as your single means for ad hoc queries.
Yeah, exactly. Huh?
So I've got a couple questions about that. It's the query language is, you probably said it and I haven't all but it's not compliant SQL.
It's pretty close. Yeah, so it's pretty much the same as what Hive SQL is. And Hive is, I guess to put it another way, like in the world of BI, it's definitely pretty well understood, I guess, if that makes sense. So for me personally, as a software developer, I don't love SQL all the time, right? And there's some other things that I prefer, but for like the BI world, it's pretty well understood, and I think most people are kind of ask those questions. On the other thing that you kind of get on top of that, that I didn't really touch on here, is that ability to sort of still also query on nested data structures. So you can kind of still, there are some little extensions in terms of SQL to be able to sort of deal with these nested data structures.
So, there's no question about that. So, in order for them to be able to query that data though, you had to take it from wherever it was.
Right.
Put it into Parquet format, right? So, and then if you're going to support ad hoc querying, then doesn't that mean you're going to want that data set to be accessible all the time?
Yes.
The use case we talked about before was, I don't want to have this data warehouse running all the time. I just want to bring it up and actually have to ask some questions on it. But you've got a separate team now that's doing their own things as they need to do all the requirements we need to need that data to be available to them on demand.
So it is, but I mean, I guess the difference is it's just on S3.
Yeah, right, they can be stored on this.
So my question is then, if you're going to take the data from wherever it is and reparse it into something else, what is the reason that you would reparse it into Parquet format and use Presto to query it rather than reparse it into Cassandra and use SQL to query it or Elasticsearch to index?
Yeah, and
or
like it's by no means it's not a panacea, right? Like it's not like the end. There's definitely still plenty of cases where other layers or other ways of storing the data make more sense, right? Like it's still one of those things where this is really sort of this interactive ad hoc analysis that may happen a couple of times a day, where say maybe just the cost of whether it's Redshift or whether it's Cassandra is pretty high, right, to keep it in Discord.
Yeah.
It's just that it makes more sense and you get most of it, a lot of the same query points out of it, right? But like as far as what this sort of, you will notice is that there's still sort of the ETL process that exists, right? Like you don't get away from just sort of the having to do the transformation. And this kind of gets into a lot into like Lambda architectures and a lot of like, I don't know how many of you are like, have played around or read about like Lambda architecture. That's sort of like the direction we're moving, is to truly try and be doing making these transformations much easier. And that's one of the things that you kind of get out of Lambda architecture in terms of being able to sort of just hook on to the log and, you know, transform as it's going, right? And that's kind of the world that we're trying to get to. It's going to be a long road.
So Parquet seems like the winner here, and really the magic of this talk is Parquet.
Parquet. That's Presto is still really, really good, but yes, Parquet is what.
Question is, does Parquet support like live updates such that you can ETL all your data into Parquet, and then as new data comes in, you can just append to Parquet?
You can append, but you wouldn't want it. You want to do it on some window that makes sense, right? So like generally how most people are going to do this is they're going to choose some window of updates. And you might say that window is like 10 minutes or something like that. Basically means your like data warehouse is going to be 10 minutes trailing behind. But essentially what happens is you just like, you append it and then sort of rewrite that metadata or write two metadata files, and then it will take care of like looking at both and say, oh, I know we can do this here. So that's, yeah, it's definitely like updates are, you're not, I mean, this is like everything with data warehousing. You just don't get awesome, bright performance, you know, like that's what we do, right? We take the cost of writes for easy reads. If that makes sense. So go ahead.
When you have an analyst that says, hey, I want to run a query now, what's the latency for them to spin up a EMR cluster and get kind of before they can even run the query?
Yeah, so like EMR is like 15 minutes, so that's not awesome. One of the things that we're probably going to be doing is trying to get away from EMR, not for that use case, but for other use cases where EMR doesn't give you quite as much HA as we need. But at a certain point in time, like the hope is that, hey, we at least have some bare bones amount of this always provisioned, right? Like maybe 2 or 3 nodes or whatever. And as they sort of start to be doing more things, that we can sort of auto scale that, right? Because we get that flexibility now with the system where we don't have like, you know, a repartition we need to do with the data, like on disk. We just sort of bring up new nodes and sort of say, okay, we brought up a whole bunch of nodes because our query queue got quite long. and then we can sort of do that scaling. That's going to be a long way off for us. So right now the cost is like, yeah, there is like a 15-minute window or whatever where there's got to wait
And so
around.
you built some sort of interface for these guys? So
We're like, mostly they are going to own most of this stuff for it. Like, this is, like I said, I'm kind of a platform team. Like, that's where we hope to be at some point in time. Right now, it's like, hey, we've written all this stuff out in Parquet for you. Here's some scripts to help you provision clusters. Go at it. And we have a smart BI team and they make it work. But at some point in time, like our platform will probably include things like that to sort of have the nice, that nice thing. There's actually some open source projects that kind of do that. I think Airbnb is the one I think I have it, like a front end for querying Presto that you can sort of just let it know about your clusters, and then it will give them a nice interface for querying in a web browser and saving results sets out.
So 15 minutes is if you already have it in Parquet. If they ask a query that isn't yet in Parquet, are you guys just skipping and going straight to Redshift? But my end question is, realistically, how long is the ETL from existing data into Parquet if you have to do that?
Yeah, I mean, so like so to give you a sense, this is going to be, so right now, like our ETL that we do for Canvas, our big product, takes us about 4 hours, and we're doing it on like a nightly tick.
Yeah.
So we process something like 2 terabytes of data in 4 hours. That's using Spark, and we do that pretty fast. So this is the other, like this is kind of where I was talking about before, like the world of like Spark and Hadoop and all these things. That's also getting much, much faster, right? Like it's actually really quite good for how little optimization we've done against it to be detailing that much data in about 4 hours. We are moving towards, as part of like our model of like land architecture, towards doing these incremental ETLs such that we'll just be at some point taking the like Postgres logical replication log, right, and using that, writing it into Kafka Kinesis, and then just taking a window over that, and that then becomes our bigger window is that then becomes we have to do that chunk of work in that time, and then we're just 10 minutes delayed against real time, right? Like at some point in time, that's where we hope to get at.
So right now it's daily batches on about 2 terabytes in 4 hours. And, but now you guys are going to push so you get 10-minute increments.
Yeah, I think first it's going to be a couple hours, but at some point in time, like long term, is to sort of go for this. And this is really like this is like one of the driving forces of why Lambda architecture is sort of gaining root at a lot of places. People think about that is that at least like, and we see this at our company at scale, that like your individual like databases and single model of the data is way less interesting than your ability to sort of look at your data with different views across it and do interesting things that way, right? Like Chiquita talked about, like Google like protocol buffers floating around the place. Like from my like knowledge of Google, a lot of that is just like, oh yeah, like we've been transforming this data a whole bunch, and we rewrite this data. We have like 6 different views on this data, each one specifically tailored to this domain problem. And it really like the thing that we're like that we is like a very large code base, a very large monolithic code base. So Canvas is like a Rails project and has a ton of different tables being an LMS. Like the thing that we felt the most pain around is just that like one single model of the relational model is getting to be incredibly difficult for us to scale, not necessarily operationally, but organizationally in terms of like being able to create new features properly without doing stuff like the pain of database migrations now that we have a whole bunch of shards, now we have like shards for like 60 database clusters running, right? Like it gets to be very, very difficult. So like our move towards microservices is also just as much about not necessarily the applications, but also being able to split up the data layer such that we can treat the data layer more in the use case that is interesting. But like I said, part of that is we still have to be able to do these data warehousing things. We still have to be able to like answer questions across the data in aggregate, and that's where we're feeling it's going to be good for part A and stuff. Cool. Any other questions? Did I inform you at least a little bit? Yeah. Okay, cool. Thanks, Linda. Oh, and also we're hiring if anybody is someone related to this. I was just to say that, right?
You can say that if you'd like. that's, I mean, I think everyone's hiring.
I know.
Really like it. Instructure is a great place. You should come work at Space Monkey, but Instructure is a great place.
So when are you guys gonna use Space Monkeys as a great replacement?
Maybe after it's launched. So just as far as bookkeeping for next week, or next month, I mean, next month will be a paper, sort of more focused on papers, and then the following month will be a system. I'm looking for speakers, so if anyone has any interest in just sort of talking and learning about something and then presenting on it, many of our talks that have been at this meetup have been prepared by people who learned about the topic after agreeing to give the talk. So if that's something that sounds interesting to you as far as a forcing function to learn about a distributed system, some of the suggestions that I have for next week are Microsoft has a great paper called FDS, the flat data center storage system. It's interesting because a lot of data centers have sort of a hierarchical network topology. And so Microsoft sort of asked the question, how can we rearrange a storage system to better utilize a network where the throughput between all peers is really fast? So if you just pay a little bit more to have a better network topology instead of this hierarchical one, what can you do? So that's a really interesting paper. Chain replication is another paper that I think would sort of be interesting to cover. That one is just sort of a way of getting good properties around replication. There's two sort of like, they're not really academic papers, but there's two sort of posts that would be good as far as like intuition about distributed system design. The first one is The Tail at Scale, which is a Jeff Dean Google post about how they deal with long tails at scale. There's another paper called There Is No Now, which talks about time simultaneity in distributed systems, which would be a great paper for us to cover and talk about. There's another system called Sinfonia, which is essentially a distributed system where the main property is mini transactions. That'd be a great one to cover. Paxos, I think we've covered Raft already, but not on any recorded format, so Paxos might be interesting. Paxos is intimidating. Everyone sort of thinks of Paxos as this really complicated distributed systems protocol, but it's actually not. It's actually like for at least single value single decree Paxos is actually pretty straightforward and would be totally coverable by someone who's learning it for the first time. So if any of those sound interesting to you, please come and talk to me. For the following month, I'm hoping that someone will want to talk about Ambry, which is LinkedIn's distributed storage system that they just open sourced this week. I'd love to learn more about that. So if no one is interested in talking, I'll probably end up picking one and doing it. But if you know someone who would be interested in talking, or if you yourself are interested in talking, or if you have another topic you'd like to cover, I am just all ears about it. So anyway, that's that. Thanks for coming, and we'll see you soon. From LinkedIn, Ambry, A-M-B-R-Y.